But this connects with something that we did earlier. So I'm going to go with centroid. Lucas, the final we haven't decided yet, meaning I haven't got, because it's going to be a common final, so we're not going to change that. So no, my vote would be to have this final on WebAssign and not on Zoom. So Lucas, if you wanted to say something before we start about that Zoom, then go ahead, unmute yourself and say or type what you got to say. I hope Lucas is there, because he asked a question and then he sort of... Lucas, you there? Oh, you know what, Lucas, my vote would be no. So if it is my vote would be no. But I don't know. If the department says yes, we're going to call them into Zoom meeting and have the WebAssign final, then yes, you might have to come to the Zoom meeting, and then you will have to start the final and so on and so forth. My thing was coming to the Zoom meeting was that some semblance of a class final, so to speak. So I saw you all started at the same time, you all ended at the same time. That was what my take was with the Zoom thing. So I could give you instructions. If you had a question, you could type it in the chat, you could ask. So this is why Zoom, but no, I'm not fond of responders. So definitely not responders next time. So most definitely not that, because responders was too much trouble. Just to block you from looking up, but then, you know, if you spend your time looking up, you will not be able to finish the test. So we can manage that way. We don't have to stop people from going to the next tab. The thing is, if you waste your time going to the next tab and looking for the answer on Google instead of solving it, it's going to cost you some questions on the test. Does that sound good? Does that sound reasonable? Does that sound manageable?
Yeah, that sounds reasonable.
So I'm just gonna go with that. But let's see. Once I know something about the final, I'll let you know. But let's start 8.3. So here we go. So centroid or center of mass. So what is this centroid? Center of mass, which I like to call COM. So I'm going to write it here. So it's COM, like our .com. And I'm going to call it that. Is the balancing point. So what am I talking about? And remember, this is kind of a different concept. So please feel free to interrupt, type in the chat if you've got some questions there. So here we go. So what do we mean by balancing point? The idea is, if I give you this kind of, I don't want to say stick, but whatever, it's a lever to balance. So if you're trying to balance it, probably you would balance this on your finger somewhere here, right? And that would be the balancing point of this one that you holding your pencil in your hand. And if you try to hold it in on the tip of your finger, then probably you could hold it like that. So I'm going to say this is the pencil or the pen that you're writing with. Now I'm just going to say to you that if I place a little eraser on this side, where will the balancing point shift? Towards the eraser or away from the eraser? Very good. So it's going to go towards the eraser. So we make our first comment. That's the balancing point moves toward higher mass. Because when you place the eraser, that end was with a higher mass, and so balancing point moves towards there. Okay, so we're going to keep this conceptually. This is what we know. This is from physics. This is from observation. This has got nothing to do with math yet. So what do we want to do? We want to find, this is not really what we want to find, but we're going to take our motivation from this. So we want to find balancing points of a system of masses. So what do? So we have 4 masses, let's say. We place them at locations. So what am I talking about? So here we go. So I have mass M1 equals 4 at point B to -3. I have M2 equals 2. Let's go with 3 masses. At point B -3, 1. And I have M3 equals 4 at B3, 5. So I'm going to have them on the coordinate system, and here we go. So here it is. So this one is at 2, -3, so that is your M1. M2 is at -3 and 1, so this is -3, this is 1. So this is your M2. And M3, which is the heaviest of them, is at 3 and 5. So 3 and 5. So I'm just going to put it somewhere here, which is your M3.
I think the graph is incorrect. Yeah.
2, -3, -3. Oh, geez. Yeah, -3 and 1. You're right. So let me change that. So this was -3 and 1, because I want to get out of this real quick. So this is M2. Is it correct now also?
Yeah.
And M3. Yeah, okay. So this is the system. And let me just draw. So this is that system of masses. And you want to find the balancing point of this system. So we define the balancing point to be X bar, Y bar. And I'm just going to say, this is what your book uses. I really, really don't like that. I'm just going to say that MX. So we use, let me just start from, so we use the idea of moment to find this centroid. So I'm going to define what moment is. Moment is, again, a physics thing. So I'm going to say moment about x-axis is defined by mass times the directed distance from the x-axis. The key word, I'm going to underline that, is the directed distance. And we're going to see what that means. My is the moment about y-axis. And it is mass times directed distance from y-axis. M is the total mass of the system. The centroid is then given by, which I will always use this formula, and that is given by my over m, mx over m. I'm going to pause, let you write, because I want your complete attention when we're doing this. So give me an indication when you're ready, and we will do this together.
And this is M subscript Y, M subscript X?
Correct. Because M subscript Y is defined up there what it is. It is the moments about the y-axis.
Yeah, I was just wondering if the M's would cancel out or not. So no.
Oh, there's something that would cancel out, but it's coming later.
Alrighty.
Mhm. So ready then?
Yep.
I'm going to go up here. I'm going to assume everybody's ready. So I'm going to go up here. I'm going to just erase this. I'm also going to erase this. And I'm just going to start writing what I wrote below. Are you going to see this problem on the test? Of course not. So here we go. Let's do that. So tell me then, the total mass of the system would be? M would be?
10.
Very good. And that is just adding the masses, isn't it? So the box was a little too big, so I'm going to just make it a smaller one. Okay, now let's talk about My. So what is My? Oh, it is the mass. So if I'm talking about this one, M1, it is the mass, which is 4, times its distance from the y-axis. So tell me, if M1 is at this location, which is what? 2 and negative 3. So this is 2, and this is negative 3. So how far is M from M1 from y-axis?
Negative 3?
From y-axis.
Oh, 2.
There we go. And that is what My is. So My is going to be 4 times 2. Then we move to the next one, which is M3, which is which is M2, which is at negative 3. So this is negative 3. And this is 1. And M3, which is at 3 and 5. So keep going. So M2 is the mass 2. Directed distance from the y-axis would be? So distance from the y-axis. So let's go get this right. So distance from the y-axis is the x-coordinate, correct?
Correct.
And what do we want? We just want the directed distance. That means we are saying distance, but if it is negative 3, then we're going to say 2 times negative 3. Very good, Trent. Plus, we go to the next one, which is 4. And I'm talking about M3 now. And the directed distance from the y-axis would be? Very good, 3. So we have what? My, in this case, and I'm just going to write those numbers here, will be 8 minus 6 plus 12. And that gives us 14. Right?
Yep.
Okay, so no questions there. So let's go ahead and compute Mx then. And you're going to tell me what Mx looks like. So Mx would be, again, the first mass, M1, which is 4, times directed distance from the x-axis, and that should be?
Negative 3.
Keep going, sir. Plus 2 times?
1.
Plus 4 times?
5.
Very good. So I'm just going to say, if you're talking about distance from x-axis, then it seems to be the y-coordinate. And so if I take those numbers and compute them, then it looks like it's negative 12 plus 2 plus 20. That seems to give us 10. So where is the centroid, the balancing point of this system? And you're saying the balancing point of this system is this My, which was 14 over 10 and 10 over 10. which means it is at 1.4 and 1. And let's see if that makes sense. So I'm going to erase the other bits in the thing. And we are saying the balancing point of this system is at 1.4. That's about 1.4. So somewhere here, and 1. 1.4 and 1. And so can we say that it seems to be tilting, it is towards, how do I know my answer is right? And I'm just going to say, oh, okay, it is more closer to the heaviest masses that were there, which was 4, and it's farther away from the lighter mass. So this is that balancing point. So I want to make a couple of comments before I go and I take questions. So why is this balancing point my over m and mx over m? I just want to point out to you that the x-coordinate of the centroid takes care of the x-coordinate, which is the distance from the y-axis. The y-coordinate of the centroid and I'm talking about the centroid. So the y-coordinate of the centroid takes care of the y-coordinate of the mass, which is distance from the x-axis. And so you have what you have there. So the idea is what? And I want all of you to completely stop writing, and I'm just going to give you a visual. I'm just going to give you an idea of what this one looks like. This might sound cruel right now, but let's be helpful. So after this whole ends, so before I start, do I have your complete attention? All of you, none of you should be writing anything. You should be just listening to me. So I can have a thumbs up or say type yes. Or, you have the emojis there, which says yes or thumbs up or something like that. So go ahead and do it for me. But I want everybody's complete attention. There you go, Russell. Say all the others. I want everybody saying yes, that you have complete attention. And then I'm going to say, well, I'm going to say that. So great. So I've got Nara, Aaron, I don't have you yet, so go ahead and give me that indication. Very good. So I have about 12 yeses from 27. So where are the others? Okay, William, Jeffrey, okay. Okay, so I'm just going to start saying this, but if you want me to pause a little bit, do let me know. But here is the idea. So I'm going to point out to this one what I'm saying here. So after this all ends, we're going to celebrate, all of us, we're going to go to the restaurant one day. In the restaurant, we're going to be served. So 3 of you are going to go with your family. What are you going to order? You're going to order 3 different dishes. So M1, M2, and M3. And because you order 3 different kinds of dishes, of course, they're going to weigh differently. So what does the waitress do? She places the dishes on a big tray like that, and she brings it to you. So what are you saying? That the balancing point, that she should be holding the tray at sort of this point to balance it all together. That's the balancing point that we are talking about. So if you want to really, really come out with, really have a restaurant that manifests this, then you should have your waiters, your staff carry a spear. Because if you go to this restaurant, what do? They put a stool, isn't it? Which has got those 4 corners. So that's not really a balancing point. And then you just put the trays on there. What you should do to really, really emphasize balancing point is they should be carrying a spear, and they should be putting this large tray on that spear. If they get the balancing point correct, then it should tray that. So that was a big joke, but I hope that you kind of got the idea of what I'm trying to say here. So this is the balancing point of a system of masses. Did that go well?
That was one of the more interesting images I've had in a while.
Okay. So looking forward to good times then. So by the way, this is the other thing that you're going to do. And I don't know, I'm just going to spoil you now. I'm going to spoil that experience for you. But whenever I go into the restaurant and then, she brings that thing and she puts the stool down and then she puts the tray on it. If she has to wiggle, then you know that she's new. She doesn't have that balancing point down. But some of them are so smooth, they'll put that stool down and they'll put the tray on there and it'll be perfect, which means what? She's got the balancing point right down. She knows that. So observe that, and that might make a different experience for you. So, but I've spoiled the total experience there. Yes, Lucas, we all have been. Yeah, I know. So, see, that would be a brand new experience for you then, going into a restaurant, being served by somebody and really, really looking at those big black trays that they carry. But is this what you're going to do? No, this is not what is going to happen. William, we're all tired of carry out. So, but this is not what we are after. What are we after? So here is what you are going to see. So we want to find the balancing point. And this is very interesting what comes out actually. Of a thin lamina. I'm going to underline the word thin lamina with a uniform density. And we're going to call that density rho. So this is rho, which is the density. So we want to find the balancing point of that. So if you're thinking, what is this lamina? What is she talking about? The paper that you are writing now, the paper, this one, the sheet that you're writing now, I'm going to say that's the lamina I'm talking about. So does it have uniform density? And the answer should be yes, it's uniform density. But then if I want to find the balancing point, then we said that the balancing point is my over m and mx over m. We're still going to use that. So now we start, but what is m? M was the mass. So mass of the lamina. So how do I find the mass of the lamina? Isn't mass density times volume? But I'm going to say, okay, I know the density. It's going to be given to me. It's uniform density, which is rho. What about the volume? And I want you to completely stop writing again. Just kind of have that and look at what I'm trying to say. So this is your lamina, which is your sheet of paper. And it's very thin. So the volume of this one is going to be the length times the width times the thickness, which is the thickness of the paper. But because of that word thin, that thickness is so negligible that I am going to estimate this volume with area. Why? Because it's a thin lamina. If it is not a thin lamina, we can't do it. Right now, you're doing this with uniform density. Go to Calc 3 and you will do it with variable density. That means the density on the lamina varies from place to place. But right now, we are talking about a thin lamina with uniform density. We are going to estimate volume with the area. So here we go. So what is mass? M is going to be rho times area. And so let's look at this lamina. I mean, we look at it in terms of paper, but what is this lamina going to be for us? So here we go. The lamina is going to be given by region under the curve.
You have one.
Y equals f of x from x equals a to x equals b. I want to pause a little bit here. Any questions? Are we okay there?
Yep.
Okay, great. So I'm going to draw that lamina. So here is the lamina. I'm going to tell you to find the balancing point of this lamina. That means literally, where should I stick my finger in? And you can try it with your paper. Where should I have that finger and balance that paper? That is what we are going to find. So I'm going to say, number one, we are finding a single point. So we are finding a balancing point, which is the center of mass, which for me is COM, which is a point. That means it's got the x coordinate and it's got the y coordinate. And this is what WebAssign does. WebAssign uses this one. I do not like to use the WebAssign thing, and I'll tell you why. So I start. So what is the formula for this one? Oh, this is my over m and mx over m. So my first question to you, how to find m here? And what is m? Oh, it is rho times the area. So tell me, what is the area under this curve y equals f of x from a to b? How do you find this area? So this will be rho times
The integral from a to b.
very good, sir, f of x dx. And that's it. That is m. So when you said it was integral a to b f of x dx, and again, do not write. I'll give you time to write. What do we mean by that? When you set up the integral, what do I assume? Oh, I assumed you put this a, b into little pieces. And you are saying the area under the curve is really the sum of the areas of these rectangles, correct? Right, people?
Yep.
So let's talk about my then. So what is my? Oh, we said it was mass, which is this, times the directed distance from the y-axis. Remember, so you're saying what? My is going to be the directed distance. So it's going to be what? Mass of the strip and directed distance from the y-axis. Mass of the strip, directed distance from the y-axis. You're going to add all of them and you're going to come up with my. So can you tell me what is the directed distance of this strip from the y-axis? So what is this? What are those blue lines that I drew, which are the distance of the strip from the y-axis, or distance of your subrectangle from the y-axis? And that is going to be, so the directed distance from the y-axis is very good, Trent. It is some x indeed, and here we go. So this is going to be integral a to b, and x is between a and b. X rho f of x dx, right? Because this component is your mass. So I'm just going to say my is rho integral a to b x f of x dx. I'm just going to write a comment here. This is a constant, so I pulled it out. Why is it a constant? Because your lamina has got uniform density. It's not going to be constant next semester. But this semester it's going to be constant. So tell me, what would mx be? Remember, it's mass times directed distance This is not x, by the way, this is times directed distance from x-axis. And this is interesting. So I'm going to go all the way up there. So now tell me, what is the distance, say, of this strip from the x-axis? So I'm going to erase this. So can you tell me, what is the distance of this, all of this strip from the x-axis? Sorry.
Isn't it some y?
But here it is, but your y is not the same everywhere, isn't it? I mean, if I'm talking about this part of the strip which is very close to x-axis, then it is almost 0, right?
Mm-hmm.
If I'm going to talk about the top part of it, then what is the distance?
The arc length?
Which is y. No, you answered the first time correctly. This distance is some y, isn't it? Which is f of x. The part I'm trying to say, Russell, is that when we talked about distance from the y-axis, and I'm trying to draw these blue lines again, it didn't matter where on the strip you were. The distance was always x, whether you were at the top of the strip, bottom of the strip, or the middle of the strip. But now in your subrectangle, it depends on where you are. If you are talking about the part of the subrectangle which is very, very close to x-axis, then this part of the subrectangle, it's almost on the x-axis, it's 0. If I'm talking about the top, then it is f of x. So remind me again, when we were estimating something like that, do we take the bottom value, do we take the top value, or we take the
average?
Very good. And the average would be what? So the average would be the smallest one, which is 0, plus the maximum, which is f of x, over 2. That's the average distance.
Am I just getting mixed up and thinking it's that formula 1 over b minus a, integral a to b, f of x?
That was the average. But what was 1 over b minus a was the length of the time interval. Because, you know, when we talked about the average, Russell, what were we saying? This is your time interval. It's a period of 4 months, and you are tracking your stocks, how they behave. And they seem to go up and down. So when you were taking the average, you were dividing by the total length of the time interval, and that was b minus a. But this is not b minus a. This is what you're saying is that, okay, I've taken this region, I have divided this into little pieces. So how are you treating this each piece? You are treating this each piece as if it was this mass, m1, m2, m3, and m4, that kind of thing. So you are saying that to take the distance of this subrectangle, I'm going to squish both the sides, and I'm going to place this mass right here. And I'm going to say the distance from this, from the x-axis, is really the midpoint, the average of the two, which is f of x over 2, which is y over 2.
Got you.
Here we go. And so mx is going to be mass, which we know is rho f of x dx. The distance from the x-axis, which we know is f of x over 2. And so we're going to write mx is half rho, these are the constants, so I just took them outside, integral a to b f of x squared dx. Is everybody okay with that?
And it's squared because we're taking the two sides and multiplying them as if it were an area, or?
No, it's a squared because this part is the area. This is the density. So these two together give you the mass. And
right.
f of x over 2, this was the directed distance from the x-axis. So when you took the constants out, which were rho, which was the uniform density, and the half, which was here, what you were left with f of x times f of x dx, which is f of x squared dx.
Got you. Thank you.
No worries. How about the others? Are we okay there? And some very, very important and interesting observations. So again, I want you to completely stop writing and look at the 3 boxes. So this is your mx, this is your my, and this is your m. So I'm just going to point these 2. So tell me, when you're talking about the x coordinate, you're going to divide this box, box 1, by box 2, isn't it? You're going to divide this box by this one. So what's going to happen, you think? So if you want, I'm going to write there that you are going to go my over m, which means what? This is rho integral a to b x fx dx over rho integral a to b f of x dx. So when you take this, when you divide this, what's going to happen? What cancels? The constant cancels, right, people? When I do mx over m, what happens? The constant cancels. And what does that even mean? And I want you to, as I said, completely stop and think about this. So what are you saying? You're saying the balancing point of the lamina does not depend on the density of the lamina. It means it does not depend on what it is made up of. Then what does it depend on? Oh, it depends on the shape. So it's entirely a geometric thing now. So it doesn't matter whether it's your paper, whether it's some other material, whether it's rubber. It all depends on the shape of the lamina and not the density of the lamina. And that's one of the interesting things about this one. So we're going to say that the centroid is my over m and mx over m. Let's do an example. I'll be okay with that. Say, let's do an example and let's see how we can put this to test. So I want you to look at this one, which is a very simple example right now. So here's an example. And then we're going to up this. So I want you to find so sketch the region. Find the centroid. And I also want you to locate the centroid in the region. And what do I mean by that? Here's the example. So the region is given by y equals square root of x. As I said, this is a very, very simple example. Y equals 0 and x equals 4. So this is your lamina. So let's sketch it. So it's y equals square root of x. Y equals 0. And x equals 4. And so this is the lamina. Right? So let's start. I want to find the centroid, which I know is my over m, mx over m. Rho is the density, and I like to use that one. By the way, once I finish, I do want to make a comment for what you're going to see on the web on WebAssign. So here we go. So m is going to be. Anybody care to tell me? It's going to be m would be.
The square root of x plus 4?
Let's remind ourselves.
I'm sorry, that's the lamina.
So m is mass times area, right?
Right.
Sorry, m is density times area. So do you know density already, which is rho? Area would be, area under this curve is
the integral?
very good, sir. So go on, integral 0 to 4, square root of x dx.
Right.
And so I'm just going to say, okay, m is rho. So square root of x dx, we know this is 2/3 x to the 3/2 from 0 to 4, which is going to give us rho times 2/3 times 4 square root of 4, which is going to be 16/3 rho, and that is m. So far, so good? So I'm going to go with my. I'm writing the formula again. So my is integral rho 0 to 4 x square root of x dx. Reminding you, this is f of x, and this is the distance from y-axis. And so that gives us a rho integral 0 to 4 x to the 5/2. And so this is going to be rho 2/7 x to the 7/2 from 0 to 4. And that is going to be rho times 2/7 times 7/2 would be, f is not going to be cancelled on here. It is rho that's going to be cancelled. And I'm going to come to exactly your question, and that is what your book does. So you have a good point. If you get that, you get, I'm going to comment on it once we come to the end of it. So this is going to be 4 to the 7/2. And so that's going to be what? 2 to the 7. So this is going to be rho 2 times 2 to the 7/7, which is going to be rho times 2 to the 8/7. And that's going to be my. So did I do that correctly? Okay, so Lucas, you seem to have answered this question. So I'm going to do mx, which is rho integral 0 to 4. Remember, this is f of x squared, so this is going to be square root of x squared over 2 dx. So that's going to be mx, which is rho over 2 integral 0 to 4 x dx, which is rho over 2, and I'm just going to say 16. Sorry?
Actually, I think William might have a point. X times the square root of x is x times the square x to the 1/2, which would be x to the 3/2, correct?
Oh, geez, I integrated that here. You are right, William. So this should have been x to the 3/2. I went ahead of myself. I already integrated in my head, but yeah. So this is x to the 3/2 then. Sorry about that. And so this will be 2/5. So I'm going to make that correction right away. So this is 2/5 x to the 5/2. This is annoying when you have to grab one and the other. So this is going to be 2/5 5/2. So this is going to change, and this is going to change. So let's make those corrections. Thank you, William. So this is going to be 2/5 4 to the 5/2. So that's going to be 2/6 over 5 then. And so 2/6 over 5. All right. I think we're okay now. And I think I'm okay here as well. So this is 16 over 4 rho, which is 4 times rho. So this is mx. I'm going to pause a little bit and check my own work and let you check that one as well. So I think I'm okay. And I'm going to bring that box as well. So I'm just going to say this is what I have right now. M is 16 over 3 row. This is mx and this is my. So I'm going to get these 3 boxes, and I claim com is going to be my over m, which is row times 2/6 over 5 over 16 over 3 row, which means that gets cancelled. And I have 2 to the 6 over 5 times 3 over 16. 16 is 2 to the 4th. The other coordinate is going to be 4 row over 16 over 3 row. That gets cancelled as well. So this is going to be 4 over times 3 over 16. So I think what I claim to get is 12 over 5 and 3/4. And 12 over 5 is somewhere about, what, 2.4? So I'm just going to say this is 22.4 and 0.75. So I'm going to pause a little bit. Any questions there?
Why did we change it over to decimals?
Oh, just because I want to, what I wrote there, I wanted to locate the centroid in the region. So this was 4. So this is 1, 2, 3, 4. So I'm kind of just trying to locate it. And this we know is 2. And we said this is at about 2.4 and 0.75. So this is 1. So this is 2.4, 0.75, somewhere around here.
Ah.
And I want to visually see, does it seem like it's kind of balanced there? And the idea seems to be, yes, if you think you can, put your finger there and you have this mass of uniform density, and then you can balance it there. So Lucas, as I pointed out, the decimals are just to locate in the region. I still want your answer. See, these 2 answers are one and the same thing because it's a non-repeating, it's a terminating decimal. In other words, 12 over 5 is indeed 2.4. We are not estimating anything. We're just writing it in decimals. So for this example, it's very much okay. 3/4 is 0.75. It's just that when you have something like 12e over 5, and then when you give me, then you are estimating. Does that make sense? Or if you have something like 12 pi, then obviously you're estimating. Does that make sense? So here you're not estimating, you're just giving, both the answers are the same.
Understood.
Okay, so not bad then. So Amir, this goes to your question. So this is what WebAssign does. So WebAssign says, because row cancels anyway, we understand that because row cancels. They don't write row at all. They write row equals 1. So when you do the WebAssign homework, then you will just see that they write row equals 1. I don't like that because I like to still play with the physics part of it. Because for me, it's very ingrained that mass is density times volume. Because it's a thin lamina, volume is estimated by area. So I keep writing that row and I keep cancelling that row, telling myself that this is uniform density. But in next semester, when you go there, this is not going to be a constant. This is going to be a variable as well. And you will have to integrate that one as well. So I like to keep it, but it's up to you. You take whatever that you like there. So you are going to do WebAssign homework today, and if you think his way is right, then go ahead for that. I also think he uses kind of a different form of thing because he uses X bar and he goes, it is 1 over area times my. So he doesn't use the physics part that I like to use, but it's the same thing. So go ahead, take a look at it, and whichever one you are comfortable with, I'm okay with that. So any other questions? So, Amir, did I answer your question? Okay. So let's move on. Then we're going to, so this seems simple. This is not bad because now we are going to find COM. You are going to come up with the formulas now where your lamina is a region between two curves. And here it is. And I want you to unmute yourselves and speak now. So here it is. Here's your lamina. So it is given by y equals f of x, y equals g of x, and x is between a and b. Of course, this is a thin lamina of uniform density, which I'm going to call rho again. So yes, the formula for COM doesn't change. COM is still my over m, mx over m. The definitions doesn't change at all. My is mass times distance from y-axis. Mx is mass times distance from x-axis. The difference is mass of the lamina. And so here it is. Here is the picture. So this is your f of x. This is your g of x. X is from A to B. So I want you to set up the integrals for all of this. So tell me, what is m going to be? And as I said, unmute yourselves and say them. So m would be
So, if I recall correctly, M is density times area.
correct. An area of this, because this is your no. Go on then.
And for some reason my mind is blanking.
Okay. Anybody else? Russell doesn't have to do all the work. Very good. And Aaron, go ahead and say what would be, there we go. So this is going to be rho integral a to b. So who's the top trend? I'm going to take Aaron's response. Yes, f of x minus g of x dx. What about my? Remember, it's the mass and distance from the y-axis. So you can imagine your little subrectangles. What is a distance from the y-axis? So how would you set that up? And that's going to be very nice, Aaron. So integral rho a to b x f of x minus g of x dx. Absolutely. Keep going. Mx is going to be
Rho integral a to b f of x minus gx.
not really. Because think about this one. because this is what you got the area part down. I don't disagree with that. But then what about the distance from the x-axis? So you are talking about distance of this one, all of your subrectangles from the x-axis, from here. Yes, there should be a half, but more than that, go ahead, say it. So this will be, I agree with the part of the answers. Very nice. So it will be integral a to b, f of x minus g of x. Which part is this? This is the area part, right? And what about the distance part? How would we do that? Because you said take the midpoint, yeah? Don't take the distance to be this. And how much is this distance? The distance of the bottom of the strip from x-axis would be how much? So what is the length of this?
That'd be some y.
Very good. And what is that y? Isn't that y g of x? So what would be the length to the top? It would be
G of x plus y.
no. Look at that. From here to the red curve, what would be the distance? From x-axis to here. The distance would be, very good, Lucas, f of x. And what did we agree? We are not going to take g of x as the distance. We're not going to take the f of x. We are going to take the average, you said. So and so when we kind of do our algebra, it looks like rho over 2. Remember, this is a constant, so I pull it out. And f of x minus g of x and f of x plus g of x, isn't it f of x squared minus g of x squared dx? Just point it out.
Huh?
Sorry, go ahead, ask your question.
Isn't it a quadratic though? And
Right, so you can, if I understand your question correctly, you can just FOIL it out. So if I multiply this, this would be f of x.
yeah.
That gives me the squared. And then f of x, this would be positive, and this would be negative. So they cancel each other.
Right.
And then I have got, well, because of this negative, I've got this. And now let's do a nasty one. This is really, really nasty. But I really like this one. So let's do a nice one. You're going to see that this involves everything. So here's my example 2, and that's my last example for today. I am so happy. This is how I wanted it to be. So, by the way, this is the end of integrals. After this, on Wednesday, we are starting sequences and series. But now, in one problem, you're doing 3 integrals. So let me put this out. So this is, oh, where did my favorite one go? Okay, here we go. So I want to find the centroid of the region. That's the lamina. And that is bounded by y equals sine x, y equals cosine x equals 0, and x equals pi over 4. So let's draw this. So this is going to be y equals sine x, which is going to be, I'm going to go 0 to pi over 2. So this is going to be that one there. And cosine x is going to be, so this is sine x. Remember, you have a graphing calculator, so you don't have to, y equals cosine x. This is x equals 0. And this is x equals pi over 4. So this is the lamina. I'm going to still go with uniform density, which is rho. So what I want you to do is set up the integrals. So I want you to set up the integral for m. So go on. This one is going to be and take your time. And here, no decimals. You're only going to do decimals to locate the centroid, but otherwise I want exact answers. So here, exact answers. So set up the integral for me, people. This is going to be n equals, okay, rho, integral 0 to pi over 4. Keep going, Namir. Very good. So this is going to be, sorry. Cosine x. And as I said, I want to set those up first, and then we can. And this is very doable. What about my? And that's going to be so whenever you're ready, my is going to be
Rho 0 to pi over 4. And then it's x cosine, parentheses cosine x minus sine x dx.
very nice. So I just want to point out that when I do this integral, I'll have to use I by p, right? Because this is going to be x cosine x minus x sine x dx. So in this problem, this is I by p. This is just antiderivative because I know the integrals right away. Let's look at mx then. So mx is going to be rho
0 to pi, integral 0 to pi over 4. And this is the one that has cosine x minus sine x over 2 and cosine x sine x, or minus sine x.
So arrange everything that you said and tell me what I should write there.
I think it's
Take your
b
time.
parentheses cosine x minus sine x in parentheses multiplied by cosine x minus sine x over 2.
You're saying minus twice, if I heard you correctly. So it's going to be, I'm going to take your over 2. Yeah.
When you put it over 2, it has to be an addition.
Correct. And so when you take care of that, this is going to be what? Cosine squared x minus sine squared x dx?
Right.
And now let's start computing. So I'm going to start this one first because we wrote this one the last. So mx is going to be rho over 2. And I want you to have 2 ways of doing it. So tell me 2 ways of doing this integral. So one way would be what? How do we integrate cosine squared x again?
Can't we just switch it over to 1 minus sine squared x?
But that's not going to, remember when we said, when we integrate cosine squared x, we use the identity, don't we? Which is
Right.
1 plus cosine 2x over 2. And sine squared x would be 1 minus cosine 2x over 2. I'm going to say something else. That is one way to do it. But I'm going to say, I remember that cosine squared x minus sine squared x is cosine 2x dx. Which you can also get when you simplify this one. You should get the same thing that I got. But I don't even need that. This is just going to come out that. So mx is going to be rho over 2. Integral of cosine is going to be what? Sine 2x over 2 from 0 to pi over 4. So that's going to give us rho over 4 or if we can put rho over 2. This is going to be what? Sine of pi over 2, which is 1 minus 0. So that gives me rho over 4.
So can I just ask a question to make sure, well, to correct my thinking?
Sure.
If so cosine squared x plus sine squared x equals 1. Am I remembering that identity correctly?
Yes, you are.
So 1 minus sine squared x is equal to cosine squared x, right?
Right.
Could I use that identity and then use u sub and distribute the u into the parentheses in order to integrate?
Okay, so let's see what you're saying here. So you are saying, right, cosine squared is 1 minus sine squared x.
Right.
But then you will have minus sine squared x dx. So this will be 1 minus 2 sine squared x dx.
Oh, I was thinking to use u sub at that point, but I guess the cosine wouldn't cancel out. All right, I was wrong.
Okay, so because I was just trying to write what you were saying, and I didn't get your u sub, but I think you realized that once you write cosine squared as 1 minus sine squared x, your u sub is gone.
Right.
Yeah.
Yeah.
So are we okay with this thing? Amir, you have typed in something and I'm trying to read. So my calculator shows to be pi radical 2 over 4 minus 1. So what do we mean? What do you mean by that? So you are talking about not mx then. You're talking about something else, correct? You're talking about probably my. Okay. So mx is rho over 4. Is that everybody seems to be getting that? So we didn't do anything wrong there? I think we are okay. And the thing is, do we want to finish this? Or you are okay with us not finishing this? So I'm just trying to see if I have the answer somewhere, and obviously I don't. It's all there in the book. So, okay, let's do it now. So this is mx then. So let's go to m, which was just what? Rho integral 0 to pi over 4 cosine x minus sine x. That was the easy one. So this will be m rho. So integral of cosine x was what? Sine x. Integral of sine x is positive cosine x from 0 to pi over 4. So that gives us rho 1 over root 2 plus 1 over root 2 minus sine of 0 is 0, cosine of 0 is 1. Are we okay there? So this gives us rho 2 over root 2 minus 1, which is rho square root of 2 minus 1, and that is m. Are we okay there? Great. And let's do my then, which was rho integral 0 to pi over 4 x cosine x minus x sine x dx. So which was our I by p. So I'm going to pull this one out, and integral 0 to pi over 4 x cosine x dx would go how? So this is going to be u. This is dv. So du is 1, and v is going to be sine x, correct? And so we have u times v, which is x sine x from 0 to pi over 4, minus integral sine x dx from 0 to pi over 4. So that gives us x sine x from 0 to pi over 4 And integral of sine x is cosine x. So cosine x from 0 to pi over 4. So I'm just going to take the numerical part of it, which is going to be pi over 4, 1 over square root of 2, minus 0, plus 1 over square root of 2, minus 1. So I get pi over 4 root of 2 plus 1 over root of 2 minus 1. But remember, this is just the first part. And for mx, it's okay if I split the integrals to 2 parts. So we are splitting the integral into 2 parts long. I don't understand what you're saying, but we've got x cosine x. So mx, oh, you're talking about mx.
Yeah, it's so what I was saying is like, could I split that into like, is it the integral of 0 to pi over 4 of cosine squared x minus the integral from 0 to
Right, but
pi
if
over
you're
4.
going to split that, that's going to be a long way, because integral of cosine squared x, to integrate cosine squared x, you'll have to use this identity.
Okay.
And then you will have to take the integral of this. So the shortest route seems to be that put the identities. You know, if you kind of
Okay,
take care of
yeah.
that subtraction, you get here. Otherwise, use the identity directly, which means I know that cosine squared x minus sine squared x is cosine 2x. So this is from trigonometry. And this is the fastest way to do it. Yeah.
Yeah,
Okay.
and well, okay,
Yeah.
yeah, I missed the point there.
And as
Thank
Cecily
you.
points out, that I am already over. So I think you are just going to go integral 0 to pi over 4 x sine x, which is going to be u sub again. Take care of the numbers, and then you just have to go my over m and mx over m. So this, I like this unit because it takes you back. It takes you back to I by p. So I just want to point out one thing. You're using I by p here. You're using trigonometric integrals here. And you are using the simple antiderivatives here. So you got everything in one problem. So I think I'm going to pause. I'm going to stop, really have people go to their next class. But this is just going backwards. The only thing we introduced new was, after you find all of this, you're just going to take the ratio of my over m, that's going to be your x coordinate, and mx over m, which is going to be your y coordinate. Is that all right? So I think now, as usual, are my office hours.